Welcome everyone. This is the NPTEL problem solving session for the course Advanced Robotics. This is the session for week 7. So in the last week we had discussed about the equation of motion for robots and some methods of deriving the equation of motion, like using the Newton's equation or using the Euler-Lagrange equations. We also touched upon the recursive neural algorithm for doing inverse dynamics. And this week's lecture mostly focused on trajectory planning of serial manipulators specifically, and followed by a discussion on sensing and actuating technologies used in robotics. So what I'm going to do is I'm going to just briefly go over the planning part again and solve one or two problems with similar to the examples that Sir might have taught in class. So, and I'll also be giving some of my own thoughts about trajectory planning and some advices and some explanations of the advices you might have gotten into the lectures on as to why trajectory planning is done a particular way. Okay, so what is trajectory planning? Essentially, if we have a robot, and as usual, we'll take the example of our 2-hour robot. When we want to move, let's say, the end effector of the robot from this configuration to, let's say, this configuration, right, for any purpose, okay, so we call this configuration A and we call this configuration B. So we want our robot to go from configuration A to B, right? So intuitively we can see that we want the end effector to go along this line, right? We want the end effector to go along this particular line. So if we plan the motion to be along this particular straight line, this specific straight line, then we are planning in the end effector space. Okay. We can also say that we don't have to travel into this straight line, right? Because we just wanted to go from point A to point B, and that motion can take any form. Like, we may allow our end effector to follow any path, right? As long as it reaches the final position that we want it to be. And that is desirable, not the non-straight planning, but allowing the end effector to deviate from a strict straight line path. Why that would be desirable is because what we are controlling here, okay, are control inputs to the serial manipulator are joint torques, right? So if we look at the work done, right, by the total work done by the torques at the joints to take it from position A to B, then that total work done would be an integral of tau d theta, right, where tau and d theta are both vectors, and this is the dot product, right? This is how we calculate the work done for a revolute joint, and we do it for the complete time, right, from 0 to t. Now from this we can see that if the path in the joint space is longer, then the work done, total work done, would be higher. And like we can also say it in the reverse way, that if the path in the joint space is minimum, right, not zero, because we have to move somehow anyhow, but if the path taken in the joint space is shorter, then the work done, total work done, will also be lesser, right? And this is desirable. We don't want to enforce, let's say, a straight line path that is shorter in the Cartesian coordinates, but it leads to a longer path in joint coordinates, right? We know that the Cartesian coordinates and the joint angles are related by the mapping of forward kinematics, right? So if we say that one position is, let's say, XA, and we call the angles corresponding to it theta, okay, and the other is XB, and the angles corresponding to that we call them theta B. Right, then the distance between both, right, will be just, let's say, the norm. We take the norm for distance. It is forward kinematics theta B, right? So if we just take the distance between these, right, that does not mean that distance, like this norm, is also minimum, right? That if this is minimum, this does not imply that the joint space distance, right, or the distance between the joint coordinates is also minimum, right? If we try to see it using a graph, right, we try to plot the joint space of the robot, then let's say this point corresponds to theta A and this point corresponds to theta B, right? Now essentially, when we say that we want our robot to go from XA to XB, we actually want our robot to go from theta A, configuration theta A, to configuration theta B, right? The joint configurations. Now here we can see that the minimum path in the joint space is a straight line between these coordinates, right? But if we take a minimum of these two only, right, if we force it to go along a straight line here, then the path taken will not be a simple straight line, right? It will deviate slightly because of this non-linear mapping imposed due to inverse kinematics, right? So let's say it might take, it is not the actual path that it will take for a straight line, it is just for example. It might take this path, and you see this path is much longer compared to the straight line, right? And based on the discussion that we just had, this path will lead to more energy being consumed because the work done is larger, right? And energy consumed is equal to the work done. So that is one reason why we avoid planning in the Cartesian coordinates, right? we specify target locations in the Cartesian coordinates, but we try not to plan the motion, right? That the path that the robot joints will take, we do not specify that in Cartesian coordinates, right? We specify start position and the target position in Cartesian coordinates because that is where we want the robot to perform work, right? That is where we can specify very intuitively and very directly where we want the robot to be. Okay, so we keep this in mind that planning in, right, if I just write this also, planning in joint space leads to lower work done, right? This is lower work done. Okay, now that is one of the reasons why we avoid planning in Cartesian space. The other reasons, and apart from this reason, others are also mentioned by professor in the lectures, is that in Cartesian coordinates, all the complete Cartesian space is not accessible, right? We had a discussion about the workspace of the robot, that are the valid Cartesian space where the robot is allowed to be. Okay, so if you specify a target outside the workspace of the robot, right? Let's say this wavy region, right? The region that I've marked with this wave is the workspace of the robot, and it cannot operate outside it, right? It enters singular conditions outside these. So what that essentially means is that corresponding to that particular location, right, either this or let's say I specify here, right, that is completely outside the workspace of the robot. So it can either be outside the workspace of the robot, or even if it is inside the workspace, it can lead to singular conditions, and we do not want that, right? And if it is outside the workspace of the robot, then there is no mapping here, right? So there is no corresponding target coordinates in the joint space for the robot to go, because it does not exist, right? So that's also one of the reasons, and this also, like, we have to keep in mind while giving the target that yeah, it should be inside the workspace, right? But if let's say the target is inside workspace and we're planning in the Cartesian space, and if any point of the plan by design or due to a bug in a program goes outside the workspace, then it will lead to problems, right? The robot might break, it might burn, or it might just refuse to, let's say, like bad things can happen if we try to do this, right? So this is again another reason why we avoid planning in the Cartesian space, and there can be other reasons as well, and if you go through a book you'll find them. But the main reason that I emphasize why planning should be done in joint space is that work done in joint space, right? If we minimize the distance in the joint space, then the work done is much lesser, and that leads to an overall efficient motion of the robot, right? So now we have seen that in which space we like to draw the paths that the robot should follow, but how do we actually achieve this? How do we make these paths, right? Because it is not just about the positions, right? We because if a robot, let's say, is at rest here, right? So it is not just theta a that is specified, uh, theta dot is also specified, that initially it is at rest, and similarly, at the final position, theta dot b also needs to be specified, right? That, let's say, the robot starts from rest and the robot stops at rest, right? The velocity at start and end should be, let's say, 0. But if this has to move, then of course it needs uh, to have a non-zero velocity in between, right? And we can also go on to specify higher order derivatives, right? That, yeah, the acceleration also should be 0 at the start and end. So one of the quickest, or one of the most used way to do this kind of path planning is to use a cubic path, right? Or what we may call a cubic trajectory, right? So what we do is, for every variable, right, for every joint, we define the path as a function of time, right? And that we represent using a cubic polynomial plus a3 tq. Right now, using our initial and final conditions, right, we find out what these coefficients are. Okay, so let's say in this particular case, if theta 1, right, at a was, let's say, 10 degrees, for example, or 10 radians, let's call it 1 radian, right? And theta 1, right, we are just talking about angle theta 1 here, right? There are two angles, theta 1 and theta 2. We are just, so we have to design a different trajectory for each variable that we have, and we want to go from 1 radian to 2 radian, right? That is the target position on the theta 1 axis for theta b. And also, since we had already specified that the velocities should be 0 at start and end. Okay, so now this is the simplest specification of path that we can give, right? And since there are 4 total conditions, independent conditions that we have, so we can use a polynomial that has 4 variables, right? So it will be a fully determined, right, system, and it will basically be fully solvable. And here, since we have specified time as the parameter for this polynomial or this trajectory, so we have to also specify that what is the start time, right? Let's say t naught is 0, and what is the end time? Let's say this is 1 second. So now this whole problem can be articulated as, we want our angle theta 1 to start from rest at 1 radians, to end also at rest at 2 radians, and it should start its motion at 0 second, and it should complete this motion in exactly 1 second, right? So now we can start putting in these constraints that we have for into this equation, right? So let's say at t equal to t naught, right, and t naught is equal to 0, and we know that this is for theta 1, right? So when theta 1 0 is 1 radian, and if we put 0 here, that is equal to a naught, right? So we get our first coefficient, that a naught is equal to 1. Okay. Similarly, if I also want to specify that theta 1 at 0, okay, is 0, right? So what is theta dot? We just differentiate this. So if I just write here, theta 1 dot is a1 plus 2a2t plus 3a3t square. Okay, so this gives a1, right? So a1 is 0 in this particular case. Similarly, we applied this at t equal to tf, and that is 1 second, right? So theta 1 at 1 is 2 radian, and at 1 it is just a naught plus a1 plus a2 plus a3, right? And theta 1 dot at 1 that we want to be 0 is a1 plus 2a2 plus 3a3, right? We already know from here the values of a naught and a1, right? If we had not known these explicitly, there must have been equations, right? So there must have been linear equations, right? Coupling a naught with, let's say, a1, a2 and a3, like any combination of those. So here we have 4 variables to find out a naught, a1, a2, a3, and we would have ended up with 4 linear equations in these, right? So 4 equations, 4 independent, 4 variables, 4 independent equations. The system is solvable. So we can, if you want to try, you can also apply some basic checks from linear algebra by writing this complete system in a matrix form, right? So let's do that as well. Right, so what we had was a naught as 1, a1 as 0, and then a1 plus a2 plus a3 plus a4 as 2, no, a naught plus a1 plus a2 plus a3 as 2, and a1 plus 2a2 plus 3a3 as 0, right? If I try to write this as in the matrix form, where these coefficients of a polynomial are my variables, a naught, a1, a2, a3, this matrix will turn out to be something like this. And the right hand side will be this. Okay. So this system is now of the form Ax equal to B, where A is a square matrix, and if we check it, we're not going to do that right now, but if you check it, it is also full rank, so it is fully invertible. Right? So maybe you can directly write X as A inverse B. Right? So you can directly get all the 4 coefficients in just a single operation. Right? So either you do this or you just solve these system of equations, both are equivalent, right? You will finally end up with some values of a naught, a1, a2 and a3. And if we try to do that here, right, so this equation leads to, because a1 is already 0, right, equal to, so a2 plus a3 is 1, right, and this thing here becomes 2a2 plus 3a3 is 0. Okay, so we multiply this by 2 and subtract from this. So we get a3 as minus 2, right? Because this will become 2a2 plus 2a3 equal to, and if we subtract this will cancel out, and this will just lead to 1a3, and 0 minus 2 is minus 2. Okay, now we can put this in the equation that we got, right, here. So that would lead to, that was a1 plus a3 is 1, a2 plus a3 is 1, so it will be 1 minus a3, and it is 1 minus minus 2 is 3. Okay, so a0 is 1, a1 is 0, a2 is 3, and a3 is minus 2. So for theta 1, right, the final trajectory is 1 plus 3t square minus 2t cube, right? So this is the trajectory that is parameterized by time, right? So this is how you design cubic trajectories for, let's say, any motion, right? If you have the start and the end position and the start and the end velocities, right? It might have been possible that we had the desired non-zero velocity, right? We wanted the robot arm to kick something, let's say, at that particular position. So if we want to specify higher order derivatives, right, then we need to have a higher order polynomial to represent our trajectories, okay? Because if we try to, let's say, look at the acceleration of this trajectory at the start or at the end, right? So we write theta 1 double dot, so that becomes 6 minus 12t, right? So the acceleration here is non-zero, right, at both the times. At t equal to 0, theta 1 double dot at 0 is 6, and at t equal to 1, theta 1 double dot is minus 6. So the acceleration is non-zero. It means that the robot will not just stop moving, and if you force it to stop moving there, it will lead to jerks. When you use a cubical or a cubic trajectory, so if you want to specify these also as 0, now you have in total 6 initial conditions, right? You have total 6 constraints. So you need an appropriate trajectory with 6 that allows you 6 independent choices, right? And that would lead to a quintic trajectory. I think that is the correct name, right? Fifth order trajectory, let us call it. If we want this, it will require a fifth order trajectory, right? So let's say we at least want to specify acceleration, right? Because maybe there is some maximum acceleration that your robot or your machine can handle, that is specified by the manufacturer, and you want to specify that at most that acceleration should be used, right? You may be able to, or you may accept to handle the jerks that come due to discontinuities in acceleration curve, basically, right? But you absolutely do not want your acceleration to go above certain value. So for that, there is a trajectory with parabolic blends. Now, what does this do, right? What does this mean? So what this means is, let's say we make a graph between theta 1 and t, right? And we wanted theta 1 to go from 1 t equals 0 to 2, for example, at t equal to 1, right? We want it to go from here to here, right? So since we want to specify accelerations, we want the trajectory. Now since this is in time, that's why I'll be drawing like this. We want the trajectory to start from rest, right? So the slope here will be 0, and I want the trajectory to end at rest, 0 velocity. So the slope here also should be 0. Okay, so what I allow in this is that for a certain time I allow the trajectory to be parabolic. Why parabolic or quadratic? Is that if, let's say, my trajectory is of this form, right, then I can specify the acceleration as this, right? So for this trajectory, acceleration will be this 2a2, right? So I can, let's say, make sure that this is exactly equal to the maximum acceleration that is allowed. So that gives me one of my parameters, right? So I use that particular choice of trajectory for some time, then I use constant velocity, right? This is a straight line for some time, and then I want to stop. Then I again go through a parabolic trajectory, right? So it just blends the start and the end using parabolic trajectories, and in the middle there is this section with linear motion, right? So this kind of trajectory plan, okay, so this is a piecewise trajectory plan, okay. The trajectory plan that we did above was a continuous, whatever you want to call it, trajectory plan. This is a piecewise trajectory plan. You need to switch explicitly to a certain kind of trajectory at different times, right? And when you're specifying Amax, you can also specify your Vmax, right? The maximum velocity, because this dictates when you have to stop accelerating, right? When you have to end the acceleration region, or end this quadratic trajectory and enter this linear region, right? Because the slope of this line is the velocity that is the velocity that the robot will follow while it's approaching the target position, right? And these two values, right, the A max and V max, determine the time, right? If I call this T1 and T2, and this is our TF, we call this T0, right? This will determine what will be our T1 and T2, okay? And if we want to take a much closer look or a much deeper look into that as well, right? How does that specify or blend times, if we would call them, right? So what we'll do is we'll see how first theta 1 changes with time, that we have already seen, right? There are two blend times at the first blend time we want to start the parabolic section, and at the other blend time we want to start finishing the motion, right? So there are two parabolic sections in this trajectory. Okay, and while designing the trajectories we need to make sure that everything is continuous, right? There should not be any discontinuities anywhere. Okay, now if I differentiate this once and I draw the velocity time graph for this, what we can see is, since we know that we started from 0 and we wanted to end at 0, so at t0 and tf, the velocity theta1 will be 0. Now since this section is a constant acceleration section, right, from t0 to t1, so it means that the now since acceleration is the rate of change of velocity, that is constant, it means the velocity will rise linearly. And this is how we determine what the blend time should be, because since the velocity will keep rising, there comes a point when you reach the maximum velocity, right? In this case, theta1 dot max, that you cannot go above, right? You had a particular maximum acceleration and you have a particular maximum velocity. Okay, so let's say we reach it here. So this is your t1. So from t1 to t2, right, you just keep moving with this velocity, and from t2 you start deaccelerating. Yeah, you start decelerating till you reach again a zero velocity, right? So this is your maximum velocity, and since the slope is the acceleration, so if I just write it, the slope, the formula for the slope is the maximum acceleration, right? Because we just decided when we were using parabolic trajectories that acceleration will be constant and it will always be equal to the maximum acceleration. So this t1 in this case, because t0 we have taken to be 0, comes out to be theta1 dot max divided by a max, right? And you can also write this as theta1 double dot max, same thing, right? So this is your blend time, and this duration will be the same for acceleration and the deceleration, right, or the negative acceleration region. So t1 minus t0 is the same as tf minus t2. Okay, so now if you want to know what is the time at which you start the next parabolic section, right, or you start deceleration, you can calculate it like this, right? And we already know what is t1, so t2 is just t final minus theta1 dot max by a max, and t naught is anyway 0, and tf in our case is 1, right? But we'll just leave this in symbolic form for now, to just mark it here, and now we'll put in values, right? Now there is one requirement for piecewise, when we design piecewise trajectories like this, and we should keep this in mind always, that you might not need to accelerate the whole way, right? You might not need to reach theta dot max, right? Because if let's say you only have to mm, yeah, let's say you only have to go, let's say, a very small region from 1 to 1.2, right? And to go from 1 to 1.2, you just, right, you can make your trajectory like this, right? So you accelerate for a really small time and you just decelerate right afterwards. This is the case if you wanted to go there in the exact same time in 1 second. But let's say you wanted to go there or in half the time, right? Then, or let's say you wanted to go there in a very short amount of time, right? In before even T1 can happen, right? So you don't need to go full here, like you can just go here without reaching theta 1 dot max. You can start coming down, right? And you just end your motion here. So basically what we are trying to say is that this T2 is important, right? Because since this is time and time needs to be positive, right? Because um, we are working with causal systems everywhere, right? So time only goes forward for us, right? Time should be positive. There is no concept of negative time here right now, right? So if this blend time is more than your total trajectory time, right, it means that you don't need to accelerate for full T1 basically, right? You can just stop accelerating uh, at some point and then start deaccelerating from there, right? And if I also draw the acceleration time graph for this particular trajectory, right, so it looks something like this, that till T1 it starts from 0, since it's a discontinuous graph, right? Because we know that we chose for it to be discontinuous. From T0 to T1 it is some constant, right? Now this is where the piecewise part literally comes in. From T0 to T1 this is continuous, right? So this trajectory, right, the graph for theta 1 is C2 continuous, what we call it, right? Because it is twice differentiable. The velocity, this is C1 differentiable, right? Because only the first derivative exists, not the second derivative, right? And this is like C0 continuous. It is only made up of segments of constant accelerations, right? Just constant values, right? So from T1 to T2, when we were only going through theta dot max, then the acceleration was 0, right? This is 0 acceleration. And from T1 to T2 to Tf, right, we just used a similar negative acceleration, right? Because the magnitude of acceleration is capped, not the direction. Okay. Now again, if we keep this in mind, right, so we can actually get to know which one will come first, right? So there is a very easy way to check if we need to go the full way up to theta dot max or not, and that is if we check where is the mid point of the trajectory, right? And that is just, let's say this is Tf prime, and or let's call that also TF. If TF minus T0 by 2 is less than T1, right, then the piecewise definition of your trajectory will be different. And if it is greater than T1, then the piecewise definition will be different, right? So in this case that I just showed you, this midpoint, right, or the half time for the trajectory is more than the blend time. Okay, so in that particular case, so for TF minus T naught by 2 greater than T1, let's say call this T1 minus T0, right, the total blend time. And what is T1? We already know, right? T1 minus T0 is theta 1 dot max by A max. Okay, so if this is greater than this particular quantity, then the definition for theta 1 is T plus A to T square, basically a quadratic when time is between T0 and T1, a linear function till time is between T1 to T2, and another quadratic when time is between T2 to TF, right? So this is what I was mentioning about piecewise definition, right? Now we might be intimidated by, let's say, seeing 6 variables in this entire trajectory, but since this is piecewise, and we also mentioned that it should be continuous, right? There should be some degree of continuity, and we mentioned here with parabolic blends that there is second order continuity in the trajectory that we have just defined. So at the interfaces, right, we have to enforce that as well, right? And for these acceleration blends, we already know that these two values will be equal in magnitude but different in sign because they correspond to the acceleration of that section, right? And we also know that what is the maximum velocity, right, and that is the slope here, right? We also know what is the maximum velocity that will be achieved, that is the slope here, and that will be A3, right? And similarly, if we specify our initial velocity constraint and the final velocity at this particular parabolic blend, right? So the final velocity between time t0 to t1 is not 0. Initial velocity is 0, but the final velocity is the maximum velocity, right? Theta dot max. So using these two conditions, we can get a0 and a1, right? Two conditions, two variables. Easy. Similarly, here for this second parabolic blend, we start from theta dot max and we end at 0, right? The velocity ends at 0. So again, you have two separate conditions for a4 and a5, right? So looks intimidating, but it's not really intimidating, right? It's pretty straightforward. It is just a bunch of linear equations that just you put in initial conditions, you identify initial conditions correctly, you put in the initial conditions, and then you'll have your trajectory specified, right? Now this was for when this condition was met, right? That the half time is actually larger than the blend time, right? That we actually need to accelerate up to the maximum velocity and then come down from there, right? So in that case we needed three sections, but we also discussed a case where we do not need to go up to the maximum velocity, right? So in that case we can see that there are only two sections in velocity, right? And if we look at acceleration for that particular motion, right, theta double dot and t, it will look like this. It will be positive for some time, right? Then it will be equally negative for some time, and then it will go to 0, right? So let's try to write trajectory for this type of motion, right? For the other part of the condition. Okay, so if Tf minus T0 by 2 is less than T1 minus T0, okay, or right, this is theta 1 dot max by A max, right? So again, we saw that we only needed two segments in that case, right? So theta 1 of t in that case will be one parabolic blend plus a1t plus a2t square till time is between t naught and th. Let's call this half time, right? This is th. So till half time we use one parabolic blend, and after half time we use another parabolic blend, right, to slow down basically, right? And there is no third section, right, because you don't need any third section. Now this also, like previously we had 8 parameters here, right? But we could identify 8 conditions, and that helped us get all the 8 parameters. So here also we do have 6 conditions, right? And what are those 6 conditions? So 2 are first of all by the acceleration, right? That the acceleration for both the trajectories will have same magnitude but just different signs, right? So that is already done. Other 2 conditions are that the initial and the final velocity, right? So the initial velocity for trajectory 1 and the final velocity for trajectory 2 should be 0, right? These are the 2 conditions, and the velocity at the end of trajectory 1 and at the start of trajectory 2 should be the same. We don't know what that velocity is. We can calculate it, but let's say we don't know what that velocity is. Whatever that velocity is, it should be equal, right? And if we, let's say, if we even want to calculate that velocity, because we know that this is just the half time, right? So what will be the velocity here? Okay, because the acceleration is constant, the velocity will be just a max times th minus t0, right? So let's try to write vh, or theta 1 dot at th is just this thing, right? So here we have our 6 conditions, right? 2 from the acceleration, 2 from the initial velocity for this and the final velocity for this, and 2 for the final velocity of this and the initial velocity of this, like however you want to phrase that. Okay, so these two are pretty much very standard ways of designing trajectories in robotics. So if you want to discuss something else, then I think you should shoot an email to sir or like to any of us in any of these sessions, and we'll be happy to, let's say, discuss about this more. But this is pretty much what you will be able to get by with for this particular course and for many of the projects if you are undertaking some. Right? So now let us shift our discussion towards the other topics that were discussed this week, namely sensors and actuators. Right? So before explaining and solving some problems related to some sensors and actuators, what I would like to do is I would like to discuss the paradigm in which sensing and actuation are actually used in robotics, right? So what is a paradigm? It is just, in very crude sense, it is just a way of doing things, right? It is just a standard way of doing things, right? So the paradigm that I'm going to talk about is called the act sense, plan and act paradigm, right? And these three interact with your robot, right? So to make your robot do something, you follow all three in this particular order, right? You sense from the robot something, you plan based on what you sensed, and then you, based on your plan, you calculate what should be the actions that the robot should perform, and then you apply those actions on the robot, right? So this paradigm of sense, plan and act is very central to the idea of controlling a robot, or the idea of closed loop control of a robot, right? If you remove sensing from here, right, that you do not read anything from the robot, you just plan something and then you act on the robot, then this becomes your typical open loop control, right? But if you are actually taking, right, if you're reading something from the robot and then you are using that to plan your motion, then this becomes your closed loop, right? Closed loop control system, or like this is the paradigm that we use for closed loop control, right? So the components that help you do the sensing and the acting part are called sensors and actuators, right? So sensors help you get information from the robot, and actuators help you interact with the robot, right? Help you, let's say, push the robot forward. And this plan component is what we have actually discussed till now, right? How do you plan the motion? How do you plan a set of let's say points to be followed to go from point A to point B, right? So this sense and act, the physical components that allow you to do these things, are called sensors and actuators. and both of these are um, elements of a, let's say, a superclass called transducers, right? Now, what is a transducer? It is anything that converts one form of energy, right, to another form, right? Let's say chemical to mechanical, or mechanical to electrical, or um, any form of energy, let's say acoustic to electrical, right? So anything that converts one form of energy to another is a transducer, right? And sensors and actuators both are transducers, right? They are just different kinds of transducers. So sensors, in a typical robot that uses a digital, electrical control system, right? Uh, okay, what sensors do is they usually convert mechanical energy into electrical energy, right? Or mechanical signals to electrical signals, if you want to wrap your head around it that way, right? And actuators, they right, usually go from electrical energy to mechanical energy, because to move the robot you need to supply mechanical energy, right? Now these are just two examples of what kind of energy conversion there is. There might be actuators that take, let's say, uh, mechanical energy in one form, right? Let's say in a hydraulic form, and convert it to other form of mechanical energy, right? That is also possible, but the idea is they convert energies from one form to the other, right? So if we try to, let's say, take a look at some of the sensors that sir has mentioned in the class, right? So let's take an example of a, right, position sensor, and the most basic one that was mentioned in the class is a potentiometer, right? That, so there is this, let's say, a conductive piece of wire that is maintained at, for example, 0 volts at this end, 5 volts at this end, right? And you take another piece of conductor that can slide over this wire while making contact, right? And you just say that the voltage here is X, right? So now, of course, if this wire has a resistance R, right? If, let's say, this is a coil here and it has a resistance R, then as this conductor, right, as this conductor slides over this wire, the voltage X will change, right? Okay, so when this conductor is at this point, right, it is exactly at 0, so the voltage or X will be 0, and when this conductor is touching this extreme, right, the voltage will be 5 volts. So based on the angular position of this wiper, if you may call it, right, the voltage at X will vary. And how will it vary? Right, so we can make a linear relation for it, that X will be 5 minus 0 over voltage per radian, right? So times theta. So x is just 5 over pi times theta voltage per radian, right? So here you see this small sensor just turned this mechanical motion into an electrical signal, right, or an electrical energy. And this is what we had just discussed, sensor 2, right? They convert forms of energies, right? And in this particular case we get voltage as a signal. Now we might even get current as a signal, right? It can differ, and we might get capacitance as a signal. That doesn't matter. All of those are electrical signals, right? And in this particular case, now if we plug in, let's say theta is pi by 2, right? So what is the voltage that we'll get? It will be 5 by 2, 2.5, right? Half, exactly half. Now this, we are assuming this R is uniform, right? If this R is non-uniform, then it might not be straightforward, right? You might have to integrate it, but that is also not very difficult to do, right? So this was one of the sensors. The other type of sensors, and that is actually used very much in robotics, is relative encoders, right? So there are two types of encoders. One is relative encoders and the other are absolute encoders. Okay, so the basic difference between both of them is that relative encoders do not give positional information, right? They only give the velocity information, if you might say, right? They do not directly give velocity information, right? But they only give information about the movement of something. While absolute encoders above, like they do give velocity information, but above that they also give exact position information as well, right? And if we look at rotary encoders, right? So encoder does not need to be rotary always, right? But if we want to, let's say, measure rotational motion of a motor, for example, then it makes sense to use a rotary encoder, right? So let's say this encoder, right? This is a opaque disc and it has a slot here, right? And if you shine a light through this slot and if you start rotating it, right, and at the other end of the disc, right, if you, let's say, try to draw the side projection here, okay, so this is the side projection and a slot is here, right? So if you shine a light from here and let's say you are the one standing here, right, and you're counting how many times you were able to see the light coming through, right? So if you say, let's say, 2 times you were able to see the LED in 1 second, right? So basically you just, in this particular case, since there is only one slot, so you know that if I have seen the light 2 times, it means there must have been 2 full rotations of this, right? If we did not start directly from seeing the light, right? You get the point. So we have our omega, right? 2 revolutions, it means 2 times 2 pi divided by 1 radian per second, right? We get the speed at which this wheel is rotating, right? So this is what an encoder does. You just keep counting the number of times the light was able to pass through this slot, and you were able to see that light. You keep counting it. Now, of course, there is not a human here. There is another sensor here, right? That gives, let's say, a 1 or a 0 based on if the light is falling on the sensor or not. And this 1 and 0 we use to increase a counter, right? That keeps a track of how many times the light was seen while keeping track of time as well, right? So that essentially gives us the measurement of your angular velocity in this case, right? Now, if I want to increase the resolution, right, that I just don't want it to be updating every single rotation. I want it to be updated every 2 rotations, right? So I make 2 slots. I can make n number of slots, right? But now if I say that I could, in this particular case, if I saw, 4, 2, if I saw the LED twice, it means that I have rotated only 90 degrees, right? So essentially you divide by the number of pulses that you will get per revolution. Okay, so this is a general formula for getting the velocity for any encoder, right? For which the PPR, or the pulses per revolution quantity, is defined. And this is n, right? The number of pulses. Now, if you want to get the position value as well, then you can say that you start from 0 and then you keep updating plus omega delta t, right? You can try to keep a track of position this way, but again, since there will be some errors, numerical or otherwise, in your system, this estimate will keep on diverging, right? Let's say you write it like this, right? So basically you are estimating your position from your measurement, right? And since there is no feedback on this particular measurement, right, you're not measuring this directly, due to the errors in the system, this value will diverge from the original value, right? So you won't be able to have exact knowledge of the position of your wheel in this case, right? And that is what is solved by absolute encoders, right? So in absolute encoders, apart from having just these slots, they do have slots, but the slots are arranged in a very specific way, right? And they are arranged in a way that every sector, right? So the arrangement is very similar to the arrangement of memory on a CD drive, right? So every sector here is marked using a unique combination in binary, right? So for example, since these are 4 different signals that I can take in at once, right? So what I'll basically say is that at one time I can get 4 signals, right? 4 bits of data. Now, since I'm getting 4 bits of data, there is a total of 2 to the power 4 values that I can represent using this data, right? It means I can represent 16 values, right? So in this particular case, if I, let's say, start here and I cover all these four, right? So this particular section represents 0 0 0 0, right? And in the next section I let's say keep this one open and keep these three covered, right? So the next section, it signifies 1, right? The next section I cover this and I just keep this one open, right? So this represents a binary 2, right? Now to represent a binary 3, right, we keep these two open and we cover these, right? So now we can see, right, at every sector there is a unique representation, right? So whatever signal we get, we will be able to tell what the position of the encoder is, right? But there is one more thing that we need to pay attention to now here, is that in this particular case, since we were only taking 16 bits of data, we were only able to represent 16 values, right? It means that if we are to take from 0 to 2 pi, between 0 to 2 pi we can only represent 16 values. It means that the least count for position becomes the range divided by the total number of values, right? So 2 pi by 16, okay, so pi by 8, okay, this is approximately 0.4, right? So you cannot measure anything below this, right? You can either measure 0.4 radians or 0.8 approximately, right, in multiples of your least count only, right? So if you want to measure, let's say, 0.1 radian, that is not possible if you just use 4 bits like we have done here, right? So if you want to decrease the least count, you need to increase the resolution, right? So just increase the number of bits you use. So apart from this, I think there were some more sensors that were discussed, but I think these are like pretty much what you might actually want to learn about, and these basics is actually what is important when you're learning about sensors, right? If I have to talk about force sensors as well, then you already saw the construction of force sensor using strain gauges, right? And you could see that there were 6 values here, and in total you were using 8 strain gauges, right? So if you calibrate your sensor to get this K matrix, you could in theory just invert this matrix, right, to, or just invert this matrix to get your forces, right? Or let's say not even invert this, just use 8 measurements to get these 6 values, right? But there will be some error in this measurement because your system is over determined, right? So you basically have 6 values that you are trying to determine using 8 values, right? So it means that you have to somehow fit in the 2 extra measurements that you have here in your system, right? If this matrix K is, let's say, full row rank in this case, right? It will be a 6 cross 8 matrix, so it should be full row rank. So you're essentially mixing 8 independent vectors, right? 8 independent, 8 columns in this case, right? You're mixing them in some way to get your estimate of forces and torques, right? And again, since it's an overdetermined system, it might have some errors. Okay, and if let's say we talk about one more sensor. Okay, let's talk about ultrasonic sensor. Okay, so this is again a sensor that is of the type. Okay, so there is a class of sensors that is based on the concept of time of flight, right? So what is time of flight? Basically, your sensor sends out a signal, right? And the moment it sends out the signal, it starts its clock, right? Let's say T0. It notes that the time is T0, right? And that signal is a special signal, right? That this can also detect, right? So now it waits for the signal to come back, right? And when it receives that signal, it stops its clock, right? So these sensors, what they do is they will give you the time it took for the signal from transmission to reception, right? So if you have an ultrasonic sensor, it means it uses ultrasonic sound waves as signals, right? So now we know that the velocity of sound is, let's say, Vs in air, right? And there is some object that this signal bounced off of, got reflected, and came to our sensor, right? And this is at a distance d, right? So how do you get this distance d? You know the velocity with which the signal is traveling, because in this case it's an ultrasonic signal, and you know the total time it took, right? It means the total distance traveled, that is 2d, is velocity of sound by tf minus t0, right? So d is just velocity of sound by 2 tf minus t0, right? So this is basically how you would calculate the distance if you are using an ultrasonic sensor. If you're using a lidars or other sensors that use light, already do this for you, right? But in that particular case, the velocity will change, right? Because light travels with a different speed, right? So that this formula just changes. But this entire analysis is at its core, right? It can modify from this, you can build upon this, but the core idea of time of flight sensors remains the same. Okay. And I think in actuators, not much related to problems has been discussed, so I will not be doing that here. So I think this is enough for this week's assignments, and then I'll stop the recording and upload this video so that you guys can refer it.